During the past 4 parts of this design area videos, we explored the concept of the design area and, in particular, the density area method. As we explained, that method largely ignores the influence of walls. In this video, we'll look at another approach, one where walls and doors play a critical role in defining the design area. This approach is called the room design method, and we'll see how it can help reduce system demand and even lead to smaller pipe sizes in real projects. Before we get into the specific requirements of the room design method, it's helpful to understand why this approach is not called the compartment design method. The committee intentionally avoided that term because compartment already has a precise technical definition within the standard. Using it would have limited the method to only those spaces that meet that strict definition. Instead, they selected the term room design method, a term that is not defined in NFPA 13. By leaving it undefined, the standard relies on the ordinary dictionary meaning of room. This allows any space that qualifies as a partitioned part of the inside of a building to use this calculation method, as long as it is enclosed by walls and equipped with automatic or self-closing doors that provide the required fire resistance rating. Since the word room is not defined in Chapter 3 of NFPA 13, Section 313 requires using the ordinarily accepted meaning from Merriam-Webster's Collegiate Dictionary, 11th edition. The core principle behind the room design method is the assumption that a fire can be contained within the room where it starts. Because of this, the interior walls and doors must provide sufficient fire resistance, and the doors must be automatic or self-closing. Section 19.2333 requires that all interior walls enclosing the room have a fire resistance rating equal to the water supply duration specified in Table 19.2312. For light hazard occupancies, this duration is 30 minutes. For ordinary and extra hazard occupancies, the table lists 2 possible durations. Section 19.2313 clarifies that the lower duration values in the table are permitted only when the sprinkler system's water flow alarm and supervisory equipment are electrically supervised, and that supervision is monitored at an approved, constantly attended location. For example, in an ordinary hazard occupancy, if the sprinkler system is electrically supervised, but the supervision is not monitored at an approved, constantly attended location, the minimum required duration is 90 minutes. Therefore, to apply the room design method in that case, the interior walls must provide a 90-minute fire resistance rating. Regarding opening protection, Section 19.2335 requires automatic or self-closing doors with the appropriate fire resistance rating for all hazard classifications. However, there are 2 important exceptions for light hazard occupancies. First, the automatic or self-closing doors are permitted to be non-rated. Second, if the door is not automatic or self-closing, the room design method can still be used, provided that the calculation includes 2 sprinklers in the communicating space nearest each unprotected opening. If the communicating space contains only 1 sprinkler, then the calculation must extend to that single sprinkler. A common question is how to determine whether a room and its communicating space should be treated as separate when there is no automatic or self-closing door or even no door at all between them. Section 19.23352 provides the criteria. It states that an opening must have a minimum lintel depth of 8 inches and the opening must not exceed 8 feet in width. These requirements for lintel depth and opening width help limit how quickly a fire can spread from the room of origin into the adjacent space. When both of these conditions are met, the spaces can be treated as separate for the room design method. In that case, the calculation includes all sprinklers in the room plus 2 sprinklers in the communicating space nearest the opening. If these conditions are not met, for example, if the opening is wider than 8 feet, fire can spread quickly into the adjacent room. In that case, the 2 spaces must be treated as a single room, and the calculation must include all sprinklers in both areas. It should also be noted that if the room of fire origin has a single opening and its width is 36 inches or less, the spaces may still be treated as separate rooms even when no lintel is provided. Now let's apply the room design method to determine how many sprinklers should be assumed to operate in the hydraulic calculations. In this example, the rooms are classified as light hazard. The lintel height is 10 inches and all openings are 3.5 feet wide. The doors at these openings are not automatic or self-closing. We start with room 1. This room has only one opening to room 2. To determine the number of sprinklers in the design area, we include all sprinklers in room 1 plus the 2 sprinklers in room 2 closest to the opening. Therefore, the design area includes 4 sprinklers. For room 2, there are 3 openings to rooms 1, 6, and 8. Room 2 contains 6 sprinklers. We then add 2 sprinklers from room 1 and 2 sprinklers from room 8. Since room 6 has only 1 sprinkler, we include that one as well. This results in a total of 11 sprinklers in the design area. Room 3 has 3 sprinklers and 1 opening. To select the 2 sprinklers from the communicating space, we choose the ones closest to the opening. One of them is straightforward to identify, but sprinklers A and B in room 8 are the same distance from the opening. In these cases, we select the sprinkler that creates the greatest hydraulic demand. So we choose sprinkler A because it is farther from the water supply in this example. The total number of sprinklers for room 3 is 5. Room 4 has 1 sprinkler and 1 opening, so a total of 3 sprinklers must be considered for this room. Room 5 has 9 sprinklers and 2 openings, both leading to room 8. When multiple openings lead to the same communicating space, we add only 2 sprinklers from that space. In this example, we select the 2 sprinklers that create the greatest hydraulic demand. Therefore, room 5 requires a total of 11 sprinklers. For room 6, we include 3 sprinklers in the design area, and for room 7, we include 5 sprinklers. In our example, room 8 is a corridor. According to section 19.2337, when a corridor in a light hazard occupancy is protected by a single row of standard spray sprinklers with unprotected openings, the design area must include all sprinklers in the corridor, up to a maximum of 5. For room 9, section 19.2342 states that when an area is protected by a single line of sprinklers, the design area must include all sprinklers on that line up to a maximum of 7. It should be noted that corridors with a single line of sprinklers are limited to a maximum of 5 sprinklers because corridors typically contain minimal combustible materials to support safe evacuation. However, long rooms with a single line of sprinklers have a higher fire load, so a total of 7 sprinklers must be considered. Now that we've learned how to determine the number of sprinklers using the room design method, let's look at the other hydraulic calculation requirements associated with this approach. In this figure, 5 rooms with rated walls and automatic doors are protected by a sprinkler system. The minimum density for each room is determined using Table 19.2311. To determine the system demand, we shouldn't simply choose the room with the most sprinklers or the one farthest from the water supply. As shown in this example, room 5, with only 2 sprinklers, can still produce a higher system demand, even though it is closer to the water supply and has fewer sprinklers. All design adjustments, such as the 30% increase for dry pipe systems or adjustments for sloped ceilings, do not apply to the room design method, since these adjustments are defined only for the density area method. In other words, the room design method can still be used for a room protected by a dry pipe system, but there is no requirement to increase the number of sprinklers. Selecting the appropriate design approach, room design or density area method, depends on the room size and the number of sprinklers within each room. In this example, the room design method is more suitable for rooms 1 through 6, as it results in more efficient pipe sizing for the last 3 branch lines. However, for room 7, the density area method is more appropriate because the design area would include 5 sprinklers. In some cases, investing a small amount to meet the conditions required for the room design method can be highly beneficial. In this example, the rooms have appropriate fire resistance rated walls and doors, but the doors are not automatic or self-closing. If we recommend that the owner upgrade the doors to self-closing doors, the design area can be reduced to only 6 sprinklers instead of 24. This significantly lowers the system demand, reduces pipe sizes, and ultimately decreases overall project costs.